Dave from the Radiant Professionals Alliance. Welcome to Hydronics Talk, presentation of the Radiant Professionals Alliance. I'm your host, Mark Etherton. Here's my smiling face. The Executive Director of the RPA. I've been a member for the last 20 plus years. I'm a contributing editor to Contractor Magazine. I've been an educator for 39 years. I'm a former expert witness, still a licensed master plumber, but that's a tightly held secret because everybody says, hey, come on over and play cards. And, do you have a plunger? Sorry, I sold all my tools. Go over some quick rules of the road. If you would, please use headphones with a boom mic if possible in case we decide to bring you online. Please mute your mic to avoid feedback and background noises. Enter any questions into a Q&A typing box that will show on the right-hand side of your screen. And questions regarding this presentation will be responded to during the presentation. So if you've got something, raise your hand, get my attention, and I will stop our guest and address him with a question immediately. I would like to thank everybody for taking time to attend. Here's a picture of one of early alternative radiant panel systems that I helped develop and install in a Habitat for Humanity house on a project that was sponsored by the Department of Energy. And if you Google radiant walls, the same picture pops up on the DOE website. There's the radiant ceiling in my house up in the mountains. I'm a big fan of alternative radiant heating systems that have a lower installed cost and operate very efficiently. This is the only advertisement you'll see on this program. We'd like you to join the Radiant Professionals Alliance. You can go to www.radiantprofessionalsalliance.org and click on Join, and get you in here as a member. The talk show, basically, we have a monthly guest that comes in that we interview. We have an open Q&A session following the interview that can pertain to the subject or not. So if you've got a special question or problem, feel free to bring it forth, and we'll let our members address it. This is archived for members only for review at a later date. This is the only time that if you are a non-member that you're allowed to actually see this. So if you're here as a non-member, enjoy. If you want to see some of the other stuff that we have archived, and we've got 30 shows archived, join. Glad to show them and share them with you. The shows are meant to be fun, educational, and entertaining. I'd like for you to submit a guest interviewee to me, Mark Etherton at iatmo.org, and I will vet it and make sure that it's something that will be of interest to our members. Real quickly, here's some hydronic news that you can use. The ASSE Standard 19210 hydronic certification training is available for presentation at manufacturers reps, and qualified wholesalers. If you're interested in getting into this information, send me an email at mark.etherton@radiantpros.org, and I will respond accordingly. The AHR Expo show is coming up January 30th, 31st, and February 1st. It is in Las Vegas this year. For more information, there's the URL that you can click on to get there. In fact, our guest today will be one of our trainers at some of the training programs that we're putting on. The RPA has its fall course offering available through HeatSpring. There's the URLs on those, or you can go to heatspring.com and put RPA into their search engine, and it will bring up all the courses that we sponsor. Real quickly, let me get the lawyers out of the way. The graphics and illustrations used in this webinar are presented for educational purposes only. RPA IAPMO does not endorse or recommend the vendor, product depicted, nor any vendor or product. RPA IAPMO makes no warranties, representations, or guarantees as to, and assumes no responsibility for the products depicted, and RPA IAPMO expressly disclaims all liability for damages of any kind arising out of the use or performance of the vendor's products or services depicted. All right, here we are, Barry. Let me drag the ball of power up to you. And you are now in the driver's seat, sir. Yeah. Welcome, Barry Stephens.
Thanks, Mark. And thanks for anybody that's going to attend or view this presentation. And we're going to be talking about heat recovery ventilation, and it's got a really big application for the radiant industry because radiant generally doesn't have ventilation included. So you have to come up with a way to provide the code required ventilation in buildings. and we are re-engineering that, and I'm going to talk about that today. The way I'd like to start, there's a project that was underway, and it was developed about 5 years ago by the Northwest Energy Efficiency Alliance. And this was a program that they wanted to implement to retrofit commercial buildings. Commercial buildings has been kind of a low-hanging fruit that although there's a lot of opportunity to save energy, they haven't really had a way to get there. And a lot of commercial buildings, the typical HVAC system is just packaged rooftop units. And they're famously not efficient. And anybody in the hydronics industry is probably aware of that. And so they were looking for a piece, and this puzzle kind of shows it. They wanted an efficient rooftop HRV that could replace the ventilation component in packaged rooftop units. And there are a lot of initiatives going on to substantially reduce energy in commercial buildings. New York City has got their 80 by 50 program, and it's extremely aggressive trying to reduce the energy in buildings in New York City by 80% by 2050, and a very tall order. California has an initiative as well. Vancouver, British Columbia, also following along that same path, and a lot of decarbonization programs across the country in a lot of cities. I'm also going to talk about some code changes that are coming that are part of this initiative. So, here we go. With that, the Canadian codes have been proposed to change next year, and this looks like a pretty complicated chart, but this is for non-continuously operating ventilation systems, and you can see down in this section here, that's required to have heat recovery ventilation, energy recovery ventilation. And that's for the, in effect, lower ventilation rates. If you get into continuous ventilation, you can see that it's required in virtually all applications. So basically what this translates into is the code requirement for the entire country of Canada, with a couple of small exceptions in a couple of zones, very small zones, are going to require heat recovery ventilation or energy recovery ventilation in all commercial buildings. If you go to Washington State, as of July 1st next year, 2017, they're going to require dedicated outdoor air systems in virtually all commercial buildings. There's one exception, one big exception is multifamily, which has a different requirement. But for office, retail, education, libraries, fire stations, they're going to require dedicated outdoor air systems. So packaged rooftop, which combine heating, cooling, and ventilation, will not meet the code in Washington State as of July 1st next year. And they're requiring energy recovery ventilation with that DOAS as part of the energy efficiency standard. So things are changing, and we probably will see this spread to other places across the country as well. And that gives you an idea of the same thing. It's operating less than, the first section here, operating less than 8,000 hours, and then operating in higher levels, it's going to be required really in almost all applications in Washington State. So the idea is that the Northwest Energy Efficiency Alliance has this program that they've been looking to do, and basically it removes those RTUs, packaged rooftop units, and replaces them with a high efficiency heat recovery ventilation unit and repurposed ducts either for the heating and cooling or for the ventilation. And then right now, the program is installing ductless mini splits or VRF systems. But I'm here to tell the hydronics people that there is an opportunity to, as an alternative, replace it with hydronic heating and cooling. Because we're providing ventilation that we can control that ventilation, you can control the humidity in the ventilation air, you can manage what you need to manage, the humidity or moisture level in the air to provide hydronic heating and cooling. And ideally, a lot of these energy offices that we are dealing with, their ultimate goal is to get rid of refrigerants and VRF systems. They're not really enamored with all of the refrigerant. The possibility of leaks are actually almost sure to have leaks over time. And so hydronics would be the absolute best in their mind. So there is some opportunity there.
We know when we have a leak in our system.
Yeah, you sure do. And it usually, although it may do some damage, it's not something that lasts. You can fix it.
They can't kill you. Well, they could,
right.
But the chances are pretty slim.
Exactly. So that's we think, a real big opportunity. And I think that hydronic heating and cooling with especially ceiling radiant is something that's going to grow and present some opportunities. So this program, in a nutshell, it's taking these rooftop units. Often they're old, and we recommend doing this when they need to be replaced. And taking, as you can see, these are some pretty ugly rooftop units. This first project that we did in Portland, Oregon, had 9 RTUs on the roof, and we were able to remove 9 of those and replace it with, if you look here, this is an HRV here. There are 2 HRVs right there, and a VRF system. This is a Mitsubishi VRF system in a 2-story, 12,000 square foot building. And to give you an idea, we went through looking over on a 101 degree day on the roof. We maintained a set point of 71 degrees. The VRF never ran past its 75% of its capacity. And this number has actually been revised. I need to revise this slide, actually. We took it from 39 to 13 kBTU per square foot. That was projected in the UI. I'm going to show you a slide that shows the actual. We ended up taking it from 47 kBTU. If you replace the RTUs with a state-of-the-art RTU, we were looking at 43. We took it all the way to 13 kBTU per square foot per year. That's about 71% reduction in energy. And this chart here shows the actual temperature is the green line up above here. So the actual temperature was a little higher than modeled, and the actual energy down here, the green part of that graph, is the actual energy use. So we were modeled at a lower temperature during the summer, and we saved more energy during those same times. So the model was conservative. Our actual efficiency and gains in efficiency were greater than modeled. We've done several of these pilots. This is a historic building. This is in Seattle. It's a small office space in a historic building. And you can see, again, we significantly reduced the EUI on the space and improved indoor air quality as well. This is a third project. This is in Montana. It's a utility, electric cooperative utilities office and garage space. And one of the highlights here was, this is before we fired up the HRV using the RTUs to ventilate the space, which didn't do a very good job. And you can see what happened. We reduced the CO2. These are CO2 levels. We reduced them significantly to very manageable and healthy levels once the system fired up. So not only are we saving a lot of energy, we're also improving the indoor air quality. And that's been consistent across these projects as well. And then this is a government office, and we only did 22%, so it's a partial retrofit. That's another advantage with the whole program. This was a fairly good-sized office space, and we were able to just replace 2 RTUs with 1 HRV and provide the dedicated outdoor air system, and then a smaller VRF system that just did that space. And you can do it one section at a time based on the age of the RTUs when they need to be replaced. You can do it in phases fairly simply, just doing zones. And what's happened since, we just heard this week actually from the head mechanical engineer for the state of Oregon. This is an Oregon state office, and they're going to do the rest of the building. One thing that was really interesting was within a week of that system firing up and getting operated in that section of the building, the occupants in the rest of the building were going over there and talking to people and passing through there. And they basically said, I want what they got. So they are going to get what they got. They're planning to, they've put into the budget to retrofit the remainder of the building and finish that project out. So it's been a really positive project with a lot of positive feedback. So that's the that retrofit program in a nutshell. And the piece that was missing was a very high efficiency heat recovery ventilation unit, stand on its own, and also have the capacity to, we call this an intelligent HRV. It's got advanced controls to allow for demand control and other control options that I'll talk about a little bit later. But I worked previously with a company from Switzerland called Zender, and we were doing residential HRVs throughout North America. And they didn't want to bring their commercial units here, even though I was advocating for that within the company. And after several years of frustration with the Northwest Energy Efficiency Alliance and the Passive House community wanting those large units, the gentleman in Portland, Oregon heard that, started a company called Ventacity Systems, and brought together some really great engineers, started a company, and in about 6 months went from concept to market with what you see here, 1,000 CFM rooftop or mechanical room optional HRV. What that efficiency means, it's really important to understand this, and a lot of people don't fully understand what that efficiency increase really, how that impacts both energy efficiency and comfort in the space. Looking at this with a 40-degree outside air temperature, 70 degrees inside, the difference between a 65% recovery efficiency and 85% is the incoming air on the 65% recovery is at below 60 degrees. When you get just 20% increase in efficiency is a dramatic increase in comfort. You're going to almost 65.5, 66 degrees on the incoming air, and that means that it's a much more comfortable space. The other thing is, if you look at how much energy it takes to reheat that air from 59.5 degrees here to the 70 degrees, it's 5,667 BTUs per hour running at 500 CFM, as opposed to 2,400. So you're looking at more than double, almost tripling the amount of energy that is required to bring that ventilation air up to ambient temperature in that space. Very significant energy difference.
That reminds me of the parameters that people look at when they look at a boiler, and they go, well, I've got a boiler here that's got an AFUE of 80%, and you're trying to sell me a boiler that's 95%. That's only a 15% reduction in energy consumption, and it usually ends up being a minimum of 30. So you really can't
Yep.
trust those numbers if you see them coming in from the outside.
Right, and in the case of ventilation, it's pretty dramatic. I mean, when you look at that, when you're calculating your loads for figuring out your heating and cooling loads, that can have a dramatic impact. And one of the important points to make is that a lot of the energy modeling software is not really figuring this in very well, this very high efficiency HRVs, because they haven't been on the market. They haven't been really a factor in the development of those tools. And we're finding that they tend to oversize based on, the older, more standard efficiencies of heat recovery, energy recovery, ventilation. If you look at it in a larger perspective on different units, these are three different units. The Ventacity unit, and I won't name names here, but a couple of the better units available on the North American market. I'm showing it 85% is the low end of the Ventacity unit. 70 to 72% is the high end for anything you can find on the AHRI website. And so that is only a 15 to 13% difference. Another factor is how much energy is used by the fans, and efficient fan motors, ECM motors in our case, and efficient blades will really translate into a more efficient HRV or ERV. And the difference here, 2.9 CFM per watt as opposed to 1.3, 1.2, that's almost tripling the amount of energy, 2.5 times the amount of energy used to move the air. Some other differences I'll talk about are the controls are very important. We have a smart economizer that's included, just integrated into the system. I'll talk about that. It's also got an integrated preheater for frost prevention, frost control in cold climates. And our unit is Passive House certified, and they're North American manufacturers. There's not a single one that would get over that hurdle, which is a very high hurdle for certification by the Passive House Institute in Germany. To look at this from an energy perspective on these different units, if you look at it on the just on the amount of energy that unit will use, running at 500 CFM, I've got it at a 1/4 inch of water column. That's a low level of static, but just for comparison's sakes, I wanted to, I took what I could get. A lot of these companies will not publish a lot of information for you to do comparisons, so I had to take what I could get. But at 40 degrees, 70 degrees inside, 10 cents a kilowatt hour, which in a lot of markets is enviable. We're looking at 172 watts to run that, or 1,507 kilowatt hours per year, as opposed to 384 or 312 watts here, and pretty much double the amount of energy to run the fans. Then you look at the indoor air temperature that's coming out of those, and this is the amount of BTUs over per hour multiplied to a yearly basis on an average difference. And what you get with that 13 to 15% difference in efficiency of recovery is a more than doubling of the amount of energy that those units are going to require on a yearly basis. So it's really a significant difference in energy as well as comfort. How we do that, the most significant piece is that it is using a counterflow heat exchanger. Most of the ERVs, commercial sized ERVs in North America, are enthalpy wheel versions, and I'll talk about that in a minute. But by using a counterflow heat exchanger, you get a much better heat recovery rate than you do with wheels or with cross flow, which I'll touch on that a little bit more. but it allows for a greater surface area and a better transfer of heat on those opposing air streams. As your air is moving through here, one airstream is going in this direction through, and the other one is moving in this direction. And so through this whole center section here, they're running in opposing directions and transferring heat the whole way.
It's like a big X in the middle of the heat exchanger thing.
Yeah, and it should be, you know, we're showing here 68 degrees of coming out of the house, out of the building, and 32 degrees coming in, which is a 36-degree difference. It should be about 18 degrees of that, about halfway at the halfway point on that counterflow heat exchanger. So the 32 degrees coming in should be at about 48 degrees at the halfway point. And then, you know, it's going to be a little less than that. It's not 100% recovery, but it's going to be approaching that. Half of the transfer of energy is going to happen about halfway through. One of the important factors while I'm here is that the balance of the airflows is important for a counterflow, especially counterflow. All heat exchangers work best if you've got a balanced flow, but in a counterflow heat exchanger, in other words, if one airstream is moving at a much faster rate, more airflow through there than the other airstream, what's going to happen is that halfway point is going to be moved to one side or the other, and you're going to lose some efficiency. And we've seen that be fairly dramatic in loss of efficiency in an unbalanced flows. So that's where commissioning and balancing are an important aspect of heat recovery ventilation.
Those are important factors in any physical plant that never get done.
Yeah, and in this case, you know, having those flows actually measured and balanced is an important part of the commissioning process. That's an enthalpy wheel. So you just have one airstream, say the warm airstream moving in this direction. You have the cold airstream running down here in this direction. And what happens is the warm air heats up this material, the plate in this section of the wheel. It warms up, it comes over to this side, and then the cold air passes through and picks up that energy and warms up this airstream, vice versa. These are generally enthalpy wheels with desiccant embedded into this material. And so that if this is warm, moist air coming into this section of the wheel retains some humidity and moisture, comes down to this side, and the drier, cooler air gets warmed up and picks up some of that humidity, some of that moisture, and either retains it inside the building when you want to, or prevents it from coming in on the alternative. And then you have plate exchangers, and you've got cross-flow heat exchanger. It's kind of self-explanatory. You're not going to get as much energy transfer between those airstreams with a cross-flow. It's generally these are in the 50 to 70% recovery. A smaller cross-flow heat exchanger, it's a counterflow, heat exchanger. And when you get into a larger one with this cellular, what that is the plates that make up the heat exchanger are actually stamped and have create a cross section that looks like a checkerboard and gives you more surface area inside to transfer energy. And that's where you get up into the 85+% recovery range. Factors that will play into the metrics of performance, we call it, which is how good these heat recovery and energy recovery units are. The heat recovery rate is very simply how much heat is transferred between the two airstreams. Power consumption is an obvious thing, how much power it takes to move the air through. And in the case of the enthalpy wheel versions, they have an extra motor that turns that wheel. And so that's additional power consumption. And then something that's not talked about enough in North American circles as far as heat recovery goes is the noise level. And it's a really important factor. We found when I was doing a lot of residential work with Zehnder, and especially in cold climates, a lot in Canada, loud heat recovery ventilators get turned off. So you build a house that's really tight, well insulated, requires ventilation through a heat recovery ventilator, and then people turn it off, you can have some real problems. Indoor air quality problems, health problems, moisture problems, all just because the unit makes too much noise and people are bothered by it and turn it off at night. So it's a really important factor. And factors that play into these things, the core dimension, the bigger the core means that you're going to have more heat recovery. It's basically surface area. The other thing is by having a larger core with a lot of small channels moving through it, the bigger the hole that all those channels add up to, the less power fan power is going to be required to push the air through that heat exchanger, and that's going to result in less noise. So the core dimensions really are a big factor, and that plays into the bigger the core, the bigger the device. So the whole device volume is going to be a factor. Basically, efficient HRVs and ERVs are larger. It's pretty simple. As far as the measuring efficiency, there's a conversation going on right now, and the North American methods of measuring efficiency, the Home Ventilating Institute, HVI, which does mostly residential sized units up to 300 CFM, and AHRI, which has a listing for larger capacity, generally commercial units. They measure the incoming airstream. So you've got a situation where this intake air comes into the heat recovery ventilator. You've got potential for leakage to, if this is in a mechanical room, and you've got 30-degree air coming in to this box here, and you've got 70 degrees out here, this insulation layer is going to be important. If it's not well insulated and has a lot of thermal bridges, then you're going to influence this 70 degrees here is going to influence the temperature of this air coming into the box. Another thing is here, if you've got warm air coming out, this is your extract air coming out of the space. So this is 70 degrees, and some of this air transfers from this airstream to your incoming airstream. So from 70 degrees to 30 degrees. That's going to influence this airstream as well. And then the big thing is right there. This is a motor that produces waste heat, and that motor is basically in the airstream. And it's that waste heat is going to influence the supply air temperature as well. So you get casing leakage, you get cross flow leakage, you get motor power, waste heat. All of those things influence this. So this supply air, they refer to this as apparent sensible effectiveness. Apparently, it's really efficient. But if this motor, and the reality is this motor is also in the box and it's going to influence that. Those motor waste heat is going to have the biggest impact. If those motors use a lot of power, they're going to produce a lot of waste heat and influence this airstream and make it appear that that ventilation unit is very efficient. So all of those things play into the measurement that they do for North America. Passive house, on the other hand, is measured differently. This is the North American method here, the red line, outside air coming in and measuring the efficiency there. Passive house measures the exhaust air, and this gives you a much truer method of efficiency. Right here, if you measure that temperature of the air that leaves the building, basically, you can measure how many BTUs are going to be in that airstream very simply. 1.08 BTUs per cubic foot times the number of degree Fahrenheit degrees difference you have between outside and what's there. So if it's 30 degrees outside and this air is leaving the building at 50 degrees, that's 20 degrees times 1.08 times every cubic foot of air that goes out of the building. It can add up to a lot of energy. And to give you an idea, the difference between those two measurements, this is the passive house method. And so taking 3 different examples, this is the way passive house would measure it at about 70%. The way that AHRI and HVI would measure that, it's at 90%. So that's a great unit. It's at 90%. But the reality is you're losing a lot of energy outside of that building. Same for the second example, 95% apparently. Passive house shows it at 60%. That means that airstream leaving the building is at a fairly high temperature and a lot of energy is being lost. It can be a very close, this is a very good unit, and generally on the really efficient units that use very low fan power and very high heat recovery, that difference can be much closer. The critical thing is you can't take a standard correction. In other words, you can't take a slice out of an apple and call it an orange. It's just an apple with a slice out of it. And you can see here, this is the passive house method for measuring, and this is the HVI method. And it's all over the board. And so the only way to know that is to actually measure it and test it. Some people in the passive house community have been taking a standard correction, and it's kind of a wild card on your energy model and performance on that building. Get you to a little bit more details on this. Now, this is a chart that shows our efficiency on our heat recovery ventilation unit. But critical to this is that this is the AHRI method for measuring. And I'll show you the passive house certificate as well. But there is typically a curve on this heat recovery efficiency. And so this unit is a 1,000 CFM unit. The blue line is the heating mode. Generally, that's going to be a little higher efficiency because your delta T's on the outside and inside temperature are greater, which results in better efficiency on heat recovery. But you can see in the middle range, your efficiency is going to be, from anywhere from 400 to about 700 CFM. You've got a fairly flat line, and the efficiency is quite good. Once you get up into the higher levels, you start to drop off, and you can see it drops below 85%, or all the way down to 85% at the far end, at the high end of the capacity of the unit. We recommend that you design for heat recovery ventilation systems that their standard continuous operation be in the 50 to 70% range, so that you don't get into losing efficiency both on fan power and on heat recovery efficiency. So design to run it continuously 50 to 70%. That's a passive house certificate on our unit. So going back, you can see we're at the 85 to 93%. Passive house, we ended up at 82% on their efficiency rating. So that's important to know that can vary, and that's a typical difference, but not a standard correction. You can't take a standard correction.
Is that passive house European standards or the American standards?
Yes, that's the Passive House Germany, Passive House Institute in Germany. This is their certificate.
The real passive house.
Yep. And we're the first American manufacturer of large capacity HRVs to have passive house certification. And that's kind of a big deal. It's a very high bar to get over. It's actually a certificate. AHRI and HVI just is a testing, and it's just a listing, no matter what your efficiency is. if you look closely on this, you'll not be able to see it all, but this efficiency, the minimum is 75%. Here it shows the minimum 75% on this number. They also have 0.45 watts per cubic meter per hour on the motor efficiency, electric power efficiency, and that's a low number as well. And then they also talk about the cross-flow contamination. I talked about the transfer of air from one airstream to the other, and they have a threshold of 3% maximum, and they actually measure it at 100 Pascal differential between those two airstreams, which is not atypical of an actual system, ventilation system in a building.
It's kind of a stressed condition, isn't it?
Yeah, I mean, it's, well, you know, the HRV, if you look at it, you're going to have the fan that's doing the supply side is going to be pushing through a duct system, and at the HRV, it's going to create a very positive pressure, back pressure. So the static on the supply side is going to be a plus. On the other side, the fan is actually pulling that air through from the building, and in effect, inside the HRV, it results in a negative pressure. And so the air heat exchanger between those two airstreams is going to have the differential between the positive and the negative. So 100 pascals is a very reasonable number to look at. And that's how they test it. And then they also have sound level, which I mentioned is very critical. So they have a maximum sound level that an HRV can produce to achieve the certification with Passivhaus. So if it's got a Passivhaus certificate, you've met a high bar, and it's a very high quality unit. And fan performance, there is a fan curve, as I mentioned. And one of the critical things is that as you get into the higher, here, both high static and high volume, you're going to have a lower efficiency on your fan power. And that's, again, why we recommend that you keep it in the 50 to 70% range and try to design your ducts so that you don't have excessive static, and you'll continue to run at an efficient level. Also want to talk about HRVs versus ERVs briefly. And an HRV is heat recovery ventilation, strictly transfer of heat between those two airstreams. The heat exchanger is generally either aluminum. A lot of commercial units, as ours does, uses aluminum plates, and there are some that use plastic plates, but there's no transfer of anything but heat between the airstreams. And with an ERV, I showed the enthalpy wheel that transfers moisture, or there's, if it's a counterflow or cross-flow heat exchanger, it uses a membrane that allows moisture and heat to transfer between one airstream and the other. So in this case, this membrane would allow transfer of water vapor and heat, but not gases, contaminants. One of the things that's been talked about is formaldehyde. And the reality is, with a counterflow or crossflow with membrane heat exchanger, they are generally tested, and I know ours has been, our membranes have been tested for not transferring contaminants, formaldehyde, and so forth. So that's an important factor. But it allows heat and moisture to transfer. So on a hot, humid day, the incoming air, hot, humid air, it transfers moisture and heat to the outgoing cooler, air-conditioned, drier air. And so your incoming air is both reduced in heat and reduced in humidity. And the reverse.
Is your unit an ERV or an HRV?
Well, it's an HRV, our standard unit right now, and an ERV is under development our ERV core, we're developing a very advanced heat exchanger with this type of membrane. The best example is it's a lot like Gore-Tex. So it allows vapor but not water to transfer through. And we are developing that, and we were hoping for the AHR show to have the completed production model. I'm not sure we'll be right there, but it's in development, and the numbers preliminary are really, really good for both moisture and heat transfer on our ERV version.
Cool.
The nice thing about a counterflow and crossflow as opposed to wheels is that you can just interchange. You can pull out the HRV core and put an ERV core in, and it'll operate as either way. It gives you some flexibility. Although the cores are not inexpensive. They're a big part of the cost. To give you an idea of the difference between this on the left here is an HRV operating in a space, and then an ERV on the right. What you've got is the brown is your outdoor air, the yellow is the air coming in, the red is the exhaust air, and excuse me, this is the yellow is the exhaust air, the red is the incoming air, and the green is the exhaust. And so you can see the difference between the HRV here and the ERV. This is this triangle here is, or this, it's not a triangle, but that box there is the comfort zone for inside as far as humidity. And you can see what happens is we get a lot more in the box when we use the ERV. But you do have a little bit of reduction. You see the red dots. There's a little reduction in temperature. So you give up a little bit of thermal efficiency, but you're getting a lot more air in the box as far as the humidity goes. You have to look at this closely to get all that, but it does retain some of the humidity and keep the space more comfortable in the wintertime. In the summertime, it would work in the reverse. Okay?
Got it.
Another big factor with ventilation and heat recovery ventilation now, and I can't stress this enough, the indoor air quality and health factor is really becoming a major issue and a major conversation. And the development of the WELL building standard, other methods of measuring indoor air quality and studies in schools, and it's starting to really be a big factor. And give you an idea, this is a project that we're doing in Montana. This was the measurements before, and we're in the process of actually installing the HRVs and replacing the heating and cooling system right now. And we expect anything above 1,000 parts per million is considered to be not optimal. I'm going to share a study in the next slides that really show that. But so you can see this is a dorm, and it's above 1,000 a lot, and it's above 1,500 and all the way up to 2,000 in quite a few places. Not a really healthy space, so they're not getting good ventilation. We expect that when we do get done, we're going to be in this. This will be the top of this whole graph. It'll be somewhere in the 800 to 1,000 at the highest. And we've seen this in projects we've already done. So improved indoor air quality with continuous ventilation is important. There was just a study, this is about a year old now, but fairly recent. The Center of Excellence in Syracuse, New York, combined with the Harvard School of Public Health, Syracuse University, which is connected to the Center of Excellence, and Upstate Medical Center, were all participants in a double-blind cognitive skills study. And basically what they did was put local volunteers into their laboratory space at the Center of Excellence in Syracuse, put them at desks at cubicles in an office environment, which was actually inside their lab, and then on a double-blind basis, changed the indoor air quality basically by changing the ventilation rate, and monitored CO2 and VOC levels at varying levels, and then did cognitive skills testing throughout. And they had these people in there from Tuesday to Thursday. They left Monday and Friday out of it for obvious reasons. And so Tuesday, Wednesday, Thursday, they had them come to work for several weeks and did this double-blind testing. And what they called it was a regular day was about 1,200 parts per million on the CO2 levels. A green day was at 800 to 900 parts per million, and a green plus day was 500 to 600 parts per million on CO2. And on the green day, cognitive skills was 61% higher, and on a green plus day, 101% higher. It's very significant. So if you're in an office or you're in a school, indoor air quality and ventilation, keeping CO2 levels under control, they're starting to recognize it's really an important factor. All right. So with that, the little bit about heat recovery ventilation systems in our system. Again, it's ultra efficient, easy to install, and I'm going to talk a lot about controls. I think the controls are where a lot of systems are going. I'm sure you're all aware of that. It's happening in heating cooling systems. Ventilation, it hasn't been impacted as much, but I think it's about to be. I know it's about to be because we're doing it. So, give you an idea, this is a view of our HRV. So this is your heat exchanger. Here you have an electric preheat element. It's a 6 kW element for this unit. And here is a temperature sensor that's embedded into the heat exchanger. So we know what the temperature is inside the heat exchanger. And that's what controls the preheat to prevent frost. And it only runs on short cycles. It's modulating, and it just runs enough to keep that core temperature from developing frost. And in general, a lot less than people think. Then you have damper and supply and return side dampers. It also has hooks up to a fire system, and so automatically shut down and close the dampers in the event of a fire. And you have your motors here. These are ECM motors with advanced blades. And over here, you have the control panel right over our engineer's shoulder there. It's designed to either go on a roof or go inside a mechanical room or on a pad. And that's the basics of it.
I don't know if this has changed or not, but I know at one point in time there was some research that was being done as it pertains to fire safety, and they were actually bringing some very large fans to a house fire, and they would force oxygen into the fire, which would blow all the smoke out of the house. And it was interesting to see what the net effect was. I mean, I always thought that when you put excess air into a fire that it would have a tendency to cause the flames to get bigger, but
feed the fire.
Yeah. I mean, the show that I was watching, they would come up to a house that was on fire and set these fans right into a window and turn them on.
They weren't blowing CO2 in there, were they?
No, it was just air.
Just
it
air?
wasn't like a halon or any one of the CO2 systems that they used to dump in there.
I've never heard of that.
You never know. Maybe one of these days, the standard will be when you get a smoke alarm, 100% outside air in and pressurize the building.
We'd have that capability. So it's interesting. So real quick, the fans, blades, box is optimized, very engineered as far as the fan blades and motors go, and the way we move the air through the box. The idea is to do it very effectively and efficiently and with as little noise as possible. And that is all optimized on this system. A little bit about the efficiency as far as measuring COP. We, based on the AHRI standard test, using that, we came up with a COP of 20 in the summertime and a COP of 33 in the wintertime. And that translates, there's not a lot you can do that gives you a COP that high. And I'll talk about some other things as well that even improve on that. And that's, one is our economizer. Standard economizers just either bypass, or in the case of the wheels, they just stop the wheel from turning, and so the air comes directly in and does not really get heat exchanged. But we use what we call a smart economizer. So what we do here, this is the damper that bypasses the heat exchanger. That damper can open all the way, and you can ramp the unit up to full capacity and provide 1,000 CFM of outside air. And that's generally done if the outside temperature is cooler than the inside temperature, and the inside temperature is warmer than you want it to be. Then you simply bring directly in cool outside air. What we've done, one of the disadvantages with just opening a damper is that in the wintertime, in some spaces, especially things like schools and offices where you have a high occupancy, in a school that I was involved with in New Hampshire, it was a passive house school, so it was extremely energy efficient, very well insulated, tight, with really good windows. On a cold day in New Hampshire in January, they were actually overheating in some of the classrooms because they had 20 to 30 little heaters at their desks, and the windows were allowing solar gain. And they called us up and said, gee, we'd really like to economize and bring in some outside air. And the problem is the damper was just open or closed. And if it's 30 degrees outside, you don't want to be bringing 30 degrees through uninsulated internal ducts. You're going to create condensation on the outside of the ducts. And the other problem is throwing 30 degrees into a classroom on kids is not a good idea either. So that was a limiting factor. And they were actually having to run their heat pump system to provide some cooling in the classrooms in the middle of winter. Doesn't make sense. So we've developed a smart economizer where the bypass damper is connected with these bars here, hard connected to this louver system that's on the heat exchanger. And you can set in your controls a minimum temperature for your bypass air, say 60, 65 degrees. And this will only partially open the bypass and temper that air to that minimum set point and provide some cooling, but do it in a way that's comfortable and not going to cause any issues. So that's a unique feature to our system, and I was excited when I heard about it.
When you say 30 heaters, you're talking about the student body heat?
Yeah, 30 little heaters sitting at their desks.
What is the output of a student?
Well, it's...
I know it is for adults.
It's actually, in some cases, for kids, it can be higher than adults because of their metabolism. So it's, what is it?
I think 500 is the industry standard, and it's 350 sensible and a balanced load.
Yeah. So, yeah, somewhere in that range. I've heard 350 for kids that are, up to 12 years old, and then they apply the adult after that. But
they've obviously never tested my grandkids. They're about 1,000 each.
Well, and they're, if they're rambunctious and running around and all the rest of it, it depends on what they're doing. But, the bottom line is it's a lot of energy that's being produced in a classroom full of kids. And you want to ventilate because of the CO2 levels and all, but you want to do it in a way that keeps them comfortable. So I really was excited about this when I saw this aspect of our system.
That's a great concept. So you're just basically mixing return air with outside air to come up with a controlled cool air to be able
Right.
to help control the internal gains.
Right. We're heat recovering enough of it to keep it at a set point. And it just manages the damper and louver combination to do that. Yeah. So our system is easy to install. Very simple. Another thing, are you hearing me okay?
Yeah, I can hear you.
Okay. I didn't have that little bit of fuzzy, so I was a little worried. The very important, another feature that we have built into ours that's unique is that it's got a double configuration. So you can put it on the roof and have it duct directly through on a curb, directly into the building, which is the most efficient way to do it. And it's from a thermal perspective, the best way to do it, rather than having external ducts that have to be insulated before they go into the building. Or you can put it in a mechanical room or on a pad and run it out the side. And all it is this a panel right here that can be moved from the side to the bottom on both sides and convert it from rooftop to mechanical room. And very simply done. Comes with lifting brackets. You lift it right onto the roof. You can see this unit doesn't have its roof on. It comes with the roof in the crate, but not on. You lift it onto the roof and then very simply attach the roof assembly. Bolts right on.
I love that curved roof design too. Somebody put a lot of thought into that.
It's, yeah, you know, I've heard people say, oh, it looks kind of funny. It looks like a mailbox, you know. But the reality is most RTUs are flat topped, and so when it snows, it just piles up on top.
Yeah, that one picture that you showed with Charlie and all the rust on the top of those things. It's so typical. It's like, why don't you put a little pitch on it or something? You know, it's not that hard.
Right. So that was built in. That was part of the design. We had an amazing group of engineers that designed this from the curb up for our market in North America. So it's been real good. So we've got all on our website. We have all the details with drawings and installation information and so forth. As far as controls, this is where I'm really excited. We have some great options, and we are developing next generation as well. So it comes with a full range of control options. We have 5 temperature sensors, 4 sensors for all 4 ports, so we know the temperature of the air coming and going, and also the one I mentioned for the center of the heat exchanger. And we also have pressure sensors, and we've got a pair on each of the filters so that it actually indicates when to change the filter, which is really good on a maintenance perspective. It'll give you a heads up, filters need changing based on static. It also has those same static sensors down here. You can maintain constant duct pressure or constant duct volume based on that. So that gives you, I'm going to talk about the controls possibilities. It makes for very simple but sophisticated control options. It also has options to plug in CO2, temperature, occupancy, relative humidity, and so forth, any range of sensors on a 0 to 10 volt input sensor. And you can program those to ramp the unit up and do a range of controls. I mentioned the fire alarm, contact shutdown, filter status notification, program response sequence, so it can take feedback and respond to inputs. You can schedule it for day and time, and just like a thermostat would. So if it's in an office, you could schedule it to run on a higher level during regular office hours. And I'm going to talk about, you also can add demand control to that, so you could have it on a schedule on its regular level of ventilation, and then have it ramp up based on inputs from, say, a CO2 sensor as well, outside of that normal operating range. And you can, with the static sensing, you can maintain constant neutral or a constant plus minus or neutral building pressure. And this is a really nice feature. Mark, you and I talked briefly about, we did a project with a garage on that one pilot, and we were able to depressurize the garage and pressurize the offices so that we had no chance of getting anything of the fumes from the garage entering into that space.
Yeah, carbon monoxide's not a good gas.
No, not at all. So that's the standard control module. It's touch screen control, and that's got all the basics. You can do all the programming through that control module, but it's a lot easier to plug in a laptop with our service software and do it all on a screen with a much easier inputs through a laptop. So you can do real-time monitoring. It's got Ethernet connectivity. Our system also plugs right into a building automation systems, BACnet or similar, can be easily programmed in and put into a building automation systems. And this is some of the typical things that are on this is you've got your ventilation level, CFM, you've got your temperatures on all 4 ports. That gives you room temperature and a CO2 level if you've got a CO2 sensor incorporated.
So would this be like a dashboard screenshot that you'd see on your computer if you were
Yes.
connected by the
Yep,
internet?
that's actually taken as a dashboard.
Very
Yep.
cool. And
And
it will send you an
it's
email
pretty
if
much
the filters are plugged?
Yep.
Cool.
Yeah, it gives you and we're developing, the one thing I will mention, I'll get to it in a second. We're developing a smart building gateway that will be introduced at the AHR show in Las Vegas, and that will allow even more than anything that's been seen on a ventilation system to date. And that you could do a monthly report that gives you your filter condition, estimates when your filters will need to be changed. You can get a readout and a report on the CO2 levels in the space if you are monitoring CO2. And those are just a couple of examples, but we'll have a whole range of management controls that will be able to be produced on a regular report if you wanted, as well as remote access to the system and being able to monitor it remotely.
Very cool.
So, and it's going to be cellular based, so it's secure. We're actually having a conversation with Target stores about retrofitting some of their stores, and anybody that remembers their major data breach, it happened with the HVAC contractor's laptop. Mm-hmm. so they're a little sensitive. So we have a solution, and won't have any concern with our gateway. So this gives you a little bit idea of the controls options. So you can do just time-based. You can have it on during the day in an office, for example, and off at night, or at a low CFM. We recommend to continue to ventilate 24/7 because people aren't the only thing that produce bad things in buildings. And it's better to just turn it down to a low setting. And you also could do time and environment. So this is some of the options. You can have it ramp up to max based on CO2. You can have the level of CO2, ramp it up on steps based on that, relative humidity, the same kind of thing. You can run it at maximum based on inputs. And you also can program free cooling to a temperature set point overnight, which is a really nice feature. That's when free cooling is usually most advantageous. And you can get the building to a nice beginning set point before you start filling it up in the morning.
Cool the core down before all those heat generators show up.
Yep. as long as you get it all set with your guys doing the hydronics, right?
Exactly. It's got to be interfaced.
So yeah, we don't want to be working against each other. But that's something that our controls are really going to optimize to be able to integrate with the heating, cooling, and we feel that the development of that smart building gateway is going to be really advanced and really make for optimizing in a big way the heating, cooling, and ventilation.
Funny you should mention that. I had a call this week from my former partner that asked me what the highest groundwater temperature was I'd ever seen in Denver with ground source. And I said, well, there's a couple of hot spots out west, but, is that where you're at? And he said, no, I'm in the Cherry Creek Basin. And I said, I've never seen anything above 40 come out of the ground there. And he goes, I got 100-degree water temperatures in the ground. And I said, it's not coming from the ground. You better start looking around. Come to find out that the guy that bought the house wanted warm floors all year round. And the HVAC guy said, sure, no problem. Keep them 80, 85 degrees, wherever you want. And so the air conditioning system was running to take the heat out of the floors and sticking it into the ground source heat pump system. Whoops.
Oh, geez.
Bit of a high utility bill.
Wow. Yeah, that's really,
No
I got 100 degrees coming out of the ground, huh?
Yeah.
When you mention these things, as we are monitoring projects, our pilot projects that I started with, it has been an interesting experience, this having the capacity to do a lot of the monitoring and seeing these things. It does bring out issues, like we had that first project I talked about where we replaced 9 RTUs with 4 of our units and a VRF system. One of the offices had a, mini split or whatever they had in the office and a thermostat in there. And the temperature was uncomfortable. It was not cooling. Well, no, it was overcooling. They couldn't figure it out in the summertime. And we determined that the thermostat was right next to a lamp. And it's something simple like that. But we were monitoring it and we were able to see, something's not right here. It doesn't seem consistent with what's going on in the rest of the building. Let's go look at it. And there's the thermostat with this lamp and an incandescent bulb in it right next to it. So
had a similar situation in an apartment complex, except that it was the exact opposite. We just replaced the heating system, and this one woman kept sending messages to the office complaining that she had no heat in her apartment. And so we show up, and she's got this huge, the old CRT type of monitor that's directly below her thermostat. And I'm like, you need to move your computer. Why? I can't move the computer. This is the only place for it. And I said, well,
so to move thermostat. Yeah, but that's, it's the fact that you've got the capacity to gather data through these systems is really helping with identifying issues and problems and dealing with them.
You're seeing it with a different set of eyes than they are.
Yeah. So just a real quick go through what the capacity of the controls gives you. Simple CO2 sensor, and very simply, CO2 goes up, the unit can automatically ramp up and increase the supply to that space. That's very simple demand control. Multi-zone demand control. This is where our static sensing and constant volume, constant static can be really helpful and make for a pretty simple zone demand control. So this CO2 sensor senses a lot of people in the room, opens this damper, the static pressure of the system is dropped because of an open damper. The unit senses that and increases the volume to accommodate that. So this space with the open damper gets more air. Then this CO2 sensor kicks in, opens the damper, static drops again, the unit ramps up again, increases the supply into this space, and so forth. You could do a whole hallway full of apartments by simply having a damper for the supply and return into each apartment. So you have a supply and return trunk going down the hallway and a simple damper. We've actually looked at using a simple double car box with a damper door on one of them, and the car would set how much ventilation is going into the space, and then call it a boost. When you push a button, the damper opens and you get whatever the car is set for. Cars are constant air volume. You can set those to a set point on how much volume you're going to get, how much air you're going to get through. So we're looking at all the options. We're actually testing in our lab a lot of the dampers and so forth to optimize being able to do this system.
I bet you Belimo loves you guys.
Probably. And then multi-zone constant air volume is something that, again, we can make that simple. And when you look at the options, constant volume is just running all the time, whether its spaces are empty or full. You can do on a timer variable air volume on a program, but it really doesn't account. You're still running at this level even if there's nobody there, whereas doing demand control with CO2 or other occupancy, they're actually coming up with occupancy sensors that sense how many people are in a room now with just by their infrared signature. And we're seeing the sensors and controls on a very steep path to advancing, and the price is coming down, so it's making it much more viable to do this. And it's the best way to, and you know, from heating and cooling, it's the same way. And from a ventilation standpoint, if we can provide the right amount of air to the space when it's needed and where it's needed, it's going to optimize efficiency and maximize the indoor air quality and comfort in the space.
So the green part of the scale is basically a proportional demand program then?
Yes, driven by demand control. Generally, you know, what we usually use right now are CO2 sensors and program it to, you know, set points and provide air accordingly to keep the CO2 level at a maximum level.
I'm going to have to introduce you to my friend that has a company called ENVY, ENV Controls. And he's got a PC-based control object that can sense CO2. He's actually working with Dr. Viral Kilkus on coming up with a mean radiant temperature sensor and a whole bunch of other stuff that would fit ideally into your program. And I'm sure the two are completely compatible. As you said, you get BNC backnet controls.
Jonah Peskin, our controls engineers, would definitely want to talk to him.
Yeah.
And they probably talk in the same foreign language.
Digitals, ones and zeros.
Yeah. Jonah's very, very smart guy, came from MIT's robotics laboratory, and he's developing these controls. So definitely, he's been buying and taking apart a lot of sensors and things to see how they work and what it's all about. So that's pretty much it. The very important is that our units, when they hit the market, they have UL, CSA, and very shortly after that, this unit had a passive house certification. But on day one, we were all listed for UL and CSA, so it's compliant and able to be installed. It runs on either single phase or three-phase power. Very simple to install and hook up with the electrical, and doesn't use a lot of power, so that's a plus. All right. With that, I'm done.
Wonderful. I learned a lot. You know, I'm a wethead, but every once in a while I got to get involved on the air side. You've opened my eyes up to a lot of situations, and as we had a discussion yesterday about Robert Bean, I'm going to send him a special email once I get this thing completely rendered and loaded up onto YouTube, and have him check it out, because he is one of the most staunch believers in indoor air quality of anybody I've ever met, and he was talking about it before anybody else was even recognizing it as being an issue. So I will get him onto this and let him check it out and make sure that you two get connected at some point in time. In fact, he'll be at AHR, and if you're available on Tuesday nights, would love to have you come down to we're going to have the annual RPA social events, which is in the Westgate Hotel, and I think we're in Ballroom D. And the who's who of the hydronics industry is going to be there. I've already asked Robert to be there. I think Siegenthaler's probably going to be there. He's going to be around.
I know John. I've dealt with John and had some interaction with John.
John's a great guy. John and I have actually traveled around the world together. Spent some time over in Germany with Velo, checking out their variable speed pumps right before they introduced them to the North American market.
Huh.
Well, thank you very much, Barry. I appreciate your time in this program. I'm looking to see if I have any questions, and I don't see anything. Here is Barry's contact information for anybody that has an email that they'd like to send to him to give him any inquiries about the equipment or the applicability. Feel free to send him an email. I'm sure that he would be more than glad to talk to you about what it is that they have to offer. Does anybody have any questions? I'm not seeing any. You know what I'm going to do, though, real quickly here? Hang on just a second. Let me get my attendees up. I'm going to enable Mr. Auberchart. Kurt, you with us? Kurt to Kurt. How about Colin Wonder?
Yeah, can you hear me?
Yes, I can. How are you, Colin?
Doing well, Mark.
Good. Do you have any questions?
I don't have any questions, but very much enjoyed the presentation, Barry.
Thank you. If you come up with any, feel free, get in touch, and we'll get right back to you.
And kind of planning to be at AHR, so I'll try to stop by your booth.
Absolutely. I think you'll be very interested. We're excited. We've got some great products we're going to introduce. We've got a unit that's going to be designed specifically for school classrooms and other spaces similar, but really schools. It's a ductless unit that can install in classrooms and retrofit to provide fresh air into school classrooms. Same level of efficiency and extremely quiet. It's a unit you won't even know is there. And that, we've got a large capacity, 3,000 CFM unit we'll be introducing, and the gateway. So pretty excited. We've got about a year's worth of work to do before the end of January.
Me too.
Yeah, we're excited, but we're also working really hard.
It's going to keep you off the streets and out of the bars, Barry.
Yep, that's it.
And by the way, for those that are listening, Kurt, are you up here now? There you are. You're open. Kurt has his hand up like he's got a question. Must be something with his computer. It's not letting him talk, but anyway, it will be great to see you at the show. And for those that are here, Barry's actually going to be one of our guest panelists in one of the classes that we're doing, which is we're still picking on that no sweat radiant cooling. And Barry has a lot of experience in the ventilation requirements, obviously, for passively and actively chilled buildings. And we'll be in there with some of our other instructors putting on about an hour-and-a-half class. So if you want to learn more, make sure that you show up at AHR and meet Barry live.
Sounds like a date.
All right.
Well, thank you very much, Barry. I appreciate what you and Team Ventacity have done. Wish you good luck moving forward, and we'll do everything that we can to provide you with whatever support that we can. And I also like to thank everybody for attending. And again, if you have any questions, feel free to contact Barry at his email. And if you've got any questions for me, everybody's got my email and my telephone number. Feel free to give me a call.
Thank you all.
You bet. Have a good evening.
Much appreciated.
Take care.